s times y of 0 minus y prime of 0. That's again the Laplace transformation of y double prime of t, plus 9 y of s, which is just 9 Laplace transformation of y. Instead of writing y of t, it will be the Laplace transformation, which is y of s, equals to 0. And then you FOIL this out, and you find that s squared plus 9 times y of s minus 3s minus 6 equals to 0. And you have, oh, sorry, you FOIL this out, you have s squared plus 9 times y of s minus s times y of 0 minus y prime of 0 equal to 0. And we were given that y of 0 is equal to 3 and y prime of 0 equals to 6. So we plug those numbers in, which we get s squared plus 9 times y of s minus 3s minus 6 equals to 0. Solve for ys, we get 3s plus 6 equals s squared plus 9. And I just broke them apart. So we have 3s over s squared plus 9 plus 6 over s squared plus 9, which is equal to 3s over s squared plus 9 plus 2 times 3 over s squared plus 9. And if you recall in lecture 18, the reverse Laplace transformation, we used a couple of characteristics of common Laplace we used characteristics of some common functions that we use Laplace transformation on. So for example, Laplace transformation calls kt is equal to s over s squared plus k squared. You can see here we have 3s over s squared plus 9. So for us, the k will equal to 3. And then recall the Laplace transformation of sine kt is equal to k over s squared plus k squared, where we have here the reason why I wrote 6 over s squared plus 9 to 2 times 3 over s squared plus 9, because then I can use the characteristic down here for k equals to 3 for Laplace transformation sine kt. So to get y of t, which is what we're after at the end, we do inverse Laplace transformation of y of s. So it will be equal to the inverse Laplace transformation of 3s over s squared plus 9 plus 2 times 3 over s squared plus 9. And then I can split them into 2. So it'll be the inverse Laplace transformation of 3s over s squared plus 9 plus 2 times the inverse Laplace transformation of 3 over s squared plus 9. As I mentioned before, on the left here, you can see the common Laplace transformation functions, and then plug those in. You get y of t is equal to cos 3t, 2 times sine of 3t. And that's your answer.
Okay, great. Anyone has any questions?
Yeah, I had a
yeah.
about the cosine and sine things. You said you needed a 2 there. Oh no, I see. You just put the 2 sine. Okay.
Yeah. I factored the 2 out, so it'll be 2 times 3. So it's 2 times the inverse Laplace transformation of 3 over s squared plus 9.
I think it was because something was covering it, so I assumed that you needed like 2 times something to get sine, but I thought that wasn't the case. But yeah, it's not. So thank you.
Yeah. No worries.
Okay. Any other questions? All right. Thank you, Anshi.
Thank you.
Thank you. So Yaprak, next one.
Can you guys see?
Yes.
Okay, so I'm presenting modified question 7. So this is my function. I modified a little bit. So we need to find the Laplace transformation. So that's what I did here. I just write it down. And then I realized that I can use the linearity of the Laplace transformation. And then we can also move the constants outside, like 3 goes outside and -2 goes outside. And then like the previous student mentioned, we have like common Laplace transformations that we can use. So I realized we have like e to the at Laplace transformation. And then here we have sine kt. So in this case, k is 4, and then in this case, a is 2. So I just rewrote it like this, and then I did some simplification, and then I got this as a final answer.
The final answer read as what? I couldn't see it.
It's 12 over s squared plus 16.
Oh, okay. No,
Yeah,
on the right, on the left hand side. On the
Here?
left hand, you should write. Right, you should write L.
Oh yeah,
Laplace with parentheses f of t close
yeah, and then
parentheses.
the rest of it. Yeah, sorry.
Okay, that's okay. All right. So
Thank
anyone
you.
has any questions? Okay, all right. Thank you.
Thank you.
So Suzanne wants to present her own question.
Yes. All right, give me a second.
Okay.
Yeah, this one actually we did it. Yeah, homework. Also, you said that was going to be on the exam. You said radius and counting were not going to be on the exam.
I went to see him earlier. He was like, yeah, it's going to be a lot of graph and stuff. And I'm probably going to ask some proof solvers. I'm looking forward to that.
That he's going to put graphs on the final?
Okay. Can you see it?
Not yet.
Oh.
Did you press share content? And then
yes.
No, nothing's popping up.
Nothing.
No.
Sorry, give me a second.
Okay. Maybe while you're getting ready, maybe we can have Moses after Susan. Moses, are you ready?
Yeah.
Okay, thank you.
Can you see it?
Yes.
Okay, so it asks me to find the Laplace's transformation for cosine squared of t. And so I know that cosine of t can be rewritten into e I to the t plus e to the negative it over 2. So I did that and then I squared it. And then I separated it into like 3 parts. So 1 over 4 e to the 2 it plus 1 over 4 times e to the negative 2 it plus 1/2. And I just did the transformation for each of them individually. And I also took the limit of it instead of just the integral, because I saw it in the notes. And
yeah, that's how you do improper integrals. When you do improper integrals involves infinity, so you always try to use a dummy variable.
Yep,
Then let the variable go to infinity. Yes.
And as my final answer, I ended up getting 1 over 4 times negative 1 over 2i minus s plus 1 over 4 times 1 over 2i plus s plus 1 over 2s, and the s has to be between 0 and 2i, because each of them had their own separate what are they called? What s can be and cannot be, I guess. I forgot the proper name for it.
Where are you finished?
Yeah, sorry.
No, you went too quickly.
Oh, I went too quickly. I probably it's because I
Yeah.
skipped the actual math of the integral. So first, I just integrated, so I didn't show that part exactly. I just showed that the e's could be like combined into one thing. So the first integral would be just e times t to e to the t times 2i minus s, and the next integral would be just e to the negative t times 2i plus s to make it easier for me. And so I took the integral of that, and so I got 1 over 2i minus s times e to the t times 2i minus s. And the other one I got negative 1 over 2i plus s times times e to the negative t times 2i plus s. And I solved the transformation of 1/2 right away because it's just a constant. So it just have like the transformation of just f of t when it equals to 1 is just 1 over s. So I just multiplied that by 1/2. And then I took the limit of the e to the b times 2i minus s minus e to the 0. And the same thing for the next one. And with that, I got my answer, which is the 1 over 4 times negative 1 over 2i minus s plus 1 over 4 times 1 over 2i plus s plus 1 over 2s. And like I was saying, each of them have their own separate values of what s can and cannot be. And so overall, for those 3 different transformations, it's from s has to be greater than 0, but it has to be less than 2i.
Okay. All right. Nice. Anyone has any questions? All right.
Right.
Thank you,
Thank you.
Moses. Suzanne, are you ready?
Yes.
Okay.
Okay, can you see it now?
Yes.
Okay, so we're going to be using the Laplace transformation to find the function using the integral. So we have f of x equals to 2x plus 1, and then we'll be doing the integral of that from 0 to infinity. So,
Hold on. Your f of x equals to 2x plus 1, right?
yes.
But then your second line is also f of x equals the integral of f of x. What's missing here?
Well, I used x because we have f of x instead of, so I didn't use f of t.
Okay, so my question is, okay, I think I can draw on yours. Somehow I can draw on yours. You see, your f of x is this one, right? Now you're writing the same f of x, but you give a different thing. But those two, of course, are different.
Oh, no. Yeah, I was just trying, solving this to this. That's why I shouldn't have written f of x down there. It should be
fix this, please. Yeah, this just doesn't make sense.
It should be Laplace. I should have put the L. Sorry. I cannot change it on my screen right now, but it should be the.
I'll change it for you.
Okay.
So you want to put a Laplace of f of x.
Yeah.
Right. Now it makes sense. Okay, go ahead.
Sorry about that.
It's okay.
So we're going to find the Laplace of that using the integral. So this goes from x 0 to infinity. So it should be f of x e equals to f of s of x dx, because we're given f of x. And when I plug in my 2 of x plus 1 we have here for the f of x over here. And then I split that up to give this 2x plus 1 equation into the integral 0 to infinity e of x over here. And I just solve that over. Sorry?
Hold on a second. Yeah, hold on a second. Can you explain this line for me?
So that is just me solving the previous line. It's 2x plus 1 into e of negative xx dx. So that opens up to the 2 of x plus 1, the integral 0 to infinity ex of x dx, minus, that to give you 2x plus 1. And that's the other part right there.
Hold on a second. I'm trying to understand what you're doing here. So your variables are in x, right? There's a 2x plus 1 e to the negative sx dx, right? For this line. Then you pull out 2x plus 1 up from the integration sign. Minus derivative of this. Can you explain this to me? What are you trying to do? I don't understand.
I was trying to solve the integral for 2x plus 1 up here.
So if I do this, I would multiply 2x with e to the negative sx dx, then plus 1 times e to the negative sx dx. I would split it into that two. Then the first one, I need to do partial integration by parts. I don't understand can you explain what you are doing here? What are you trying to apply? Because my question is this, okay. This 2x plus 1 is inside the integration sign. You cannot pull out outside the integration sign. So what are some properties you are using here?
What do you mean? I put it up.
I just need to know what you're doing. I don't understand what you're doing here.
So the 2x plus 1, I have it in, I should have put a bigger bracket. I have it in here. I'm trying to find the integral of it from 0 to infinity.
No, that has nothing to do with this integration sign. The integration sign you need, so this is called improper integration. You need to use limit, right? You need to use limit to do that. Okay, you need to fix this. I'm not able to give you any credits for this. Okay. Thank you.
Okay.
You can show next time, okay? Fix it, show next time. Thank you. All right. Yinping, question 15.
Okay, I'm here and I need to upload my sorry, give me 1 second.
Yeah, it's right. Okay, some of you here, Christian, Gregory, Marquise, Rosa, Shen, Mr. Silo, Zihao, you don't present, so you're gonna lose 30% of your grades. That means you bet on the final heavily. The final is on campus. Anyway, if you have any, questions, let me know. You want to talk to me, I'm happy to talk to you to see See why you're not doing the presentations. Okay. All right.
Okay. Can you see
Go
my
ahead.
screen?
Yes, beautiful.
Okay. My question is find the inverse of the Laplace transform. So the fs is equal to 4 minus 2s over s squared plus 16. And I separate the 4 minus 2s, we get the fs equal to 4 over s squared plus 16 minus 2s over s squared plus 16. Then the inverse of fs is separate. We can inverse separate function. So it's inverse of 4 over s squared plus 16 minus the inverse of 2s over s squared plus 16. And based on the Laplace transfer of the sine kt, we have k over s squared plus k squared. Then we make k equals to 4. We have the inverse of 4 over s squared plus 16 equals to sine 40. And by the Laplace transform cosine kt, we will have s over s squared plus kt. Then let k equal to 4. We have the inverse of the Laplace transfer to s over s squared plus 16 equals to 2 cosine 40. So the inverse of the fs is equal to sine 40 minus cosine 40.
All right. Anyone has any question? I have a question. Anyone have any question? Okay. So I understand you're going from this step to this step. You're seeing I'm going to take the inverse of Laplace on the left-hand side and on the right-hand side. It's good I can write on your paper. Right. Which property gives you this? Because you take a Laplace inverse on both sides, but then you split into two Laplace inverse. So how can you do this? So which property makes you are able to do this?
The linearity.
You're reading the chat. Yaprak is trying to help you. The linearity. The linearity from where?
From the Laplace transform.
Yeah, from the Laplace transform. So this is the inverse of Laplace transform. All right. Okay, that's my only question. Anybody else has any question? Okay, thank you. So this is音频. Next one, Junyi. Also Laplace transform, question 11.
Okay. Professor, I have a question before I present it.
Yeah.
So I found like from the formula table of Laplace transform, there's like two versions of it, like where the 1 over s is equal to the L like of u of t, or the other one is L of 1 is equal to 1 over s. Which one is the correct one?
Oh, can you show me in the notes? Which page? Well, I can bring up the notes.
Well, not from the notes. I found it online. There's like a Laplace transform table. That
follow the notes, because we are in this class. Follow the notes.
Oh, okay.
Yeah, thank you.
Because
I'm sorry.
I looked for Yeah, I look for the notes also, but they're like I couldn't find out like.
Yeah, because mathematics is being developed so vastly. There's so many different things. So because you are in this class, let's just follow this one.
Yeah. Oh! It's disappeared. 1 second.
It disappeared. Right. Sorry.
Okay. So I found the 2 version of it. So I did the 2 version of the answers also. So just I presented 2 of them. So
Sure.
Let's
see
capital. Yeah, capital F of S is equal to 3 over S to find the inverse. So which is equal to the lowercase of f of t is equal to the inverse of a capital F of x. So follow the standard form. So there's 2. The L of u of t is equal to 1 over s. And the L of 1 is also equal to 1 over s. When I do a u of t, so the inverse of 1 over s, the L inverse of 1 over s is equal to u of t. So I put in the 3 over s for the inverse. So I can factor out the 3 and times the inverse of the 1 over s. So the inverse of 1 over s is u of t. So so f of t is equal to 3 times the u of t. If I follow the version of L of 1 equals to 1 over s, so which is equal to 3 times the 1 equals to 3. Sorry, I put the 1 here. It's a mistake. So either the 2 answers, the one is 3 times u of t, and the other one is 3 times 1 equals to 3.
Oh, okay. Now I see your question. What is the u of t?
Is a function of it, or
what function? Where did you find it? Because if you want to use other people's notes, you have to know what is the u of t. U of t in here just a variable.
Oh.
U of t can be anything. So in this case, your u of t has to be 1.
Okay. Okay. So
u of t
should be the variable. Okay. So the 1 should be the precise answer.
Yeah.
Okay. Thank you. Thank you. So the final answer will be the f of t is equal to 3 times 1 equals to 3.
That's right. But here you don't write. You better write the f of t.
Oh, okay.
Because it's yeah.
Thank you.
Good. You're good. So now you know. So your question has answers. And his thing is also on page 1 of lecture 18. Okay. All right. So anyone has any questions? Yeah. Yeah. Okay, good. Let's see now. That's Jean E. Albert.
Okay. This is 17.3 modified. 17.3 is fine. J3x in terms of J0x and J1x. So I just added 1 to all the numbers. Find J4x in terms of J1x and J2x, where J is the Bessel function and J4 is in the first kind with order 4. So you see that JP plus 1x equals 2p over x times JPX minus JP minus 1x. And if we need to get J4 in terms of J1 and J2, we know that we need to do it twice, because from J4, or from any number J that we start with, any order that we start with, we only go down 2, from P plus 1 down to P minus 1. So we have to do it twice. So first, when we do it for P equals 3, we get J4x equals 6 over x J3x minus J2x, because that's what comes out in the from that equation. But this is not in terms of J1 and J2, so we have to go one more. So we do P equals 2, and we get J3 of x equals 4 over x J2x minus J1x, and then we plug that J3 back into the equation we had for J4. Okay, so I did J4 of x equals 6 over x times 4 over x j2x minus j1x, close the brackets, close parentheses for the j3x we had in the j4x equation, minus j2 of x. Then when we distribute it, we get 24 over x squared j2x minus 6 over x j1x, that's a distribution, minus j2 of x, which is always outside of the brackets. Then we get j4 of x equals parentheses 24 over x squared minus 1, j2 of x minus 6 over x j1x. So that is our Bessel function of j4x in terms of j1x and j2x.
Okay. All right. Nice. Anyone has any question? So we see the Bessel's functions of first kind, the orders has relationships. All right, nice. Thank you, Albert.
Thank you.
Shu Xian, Laplace transform, question 6.
Yes. Let me see. Oh, you need to bring me to share, so.
Oh, I didn't make you presenters?
Yeah, you didn't.
Oh, okay. So I probably press on someone else.
Oh, do you see? Oh.
Yeah.
Yes, right. Find the Laplace transform of the given functions. The function is 4 minus 3t power 2. So I have the Laplace, and then this function is, and then make the Laplace this function. So according the theorem's linearity of the Laplace transform, I can write like a Laplace 4 minus, and then the this, because 3 is constant, I can bring in front of the Laplace, okay, like Laplace t power 2. So we have this one's Laplace t of a equal this gamma a plus 1 over x power a plus 1. So this one, like a Laplace 4, I can do, and then the 4 Laplace t, maybe t0 is 1. So that's why it's 4 over x. So Laplace t power 2 is like here, so here is like a 2 factorial, so over x power 3. So the answer is 2 over x power 3. So here is the final answer is 4 over x minus 6 over x power 3. That's final answer.
Okay, I like what you did here. Laplace 4 equals 4 times Laplace of t to the 0 power, which is Laplace 1.
Yeah. Yeah. That's Laplace 1. I didn't realize. I just read it. Yeah, same thing. The 1 is 1 over x, so it's 4 over x. So.
Right. Okay.
All right.
Anyone has any questions? Okay. All right. So that's a Shu Xian. Let's see. Katerina?
Yes, give me a second, please.
Okay. So after Katerina is, that's it. Katerina is the last one.
Okay. Let me know, please, if you can see it.
It's popping up, I think. Yes, now.
Okay, perfect. So I did one question. I think it's super simple. It's find Laplace transform of the function ft equals 2 for t equals or more than 0. So we have this formula, fs equals to Laplace ft, and then integral from 0 to infinity e to the power of negative st multiplied by ft function dt. So what I did first is I have a Laplace of ft equals to integral once again from 0 to infinity e to the
e to the power of negative s to t. And then we just plug in the 2, since our function of t equals to 2, to dt. We have an improper integral here, so we will take the limit with a dummy variable of b going to infinity, and I took the 2 out and have the integral of 0 to b e to the power of negative st dt. What I did next is I took, once again, 2 is out, and then when we have an e to the power of negative s to t, so we just divide it by a negative s, and then it's, oh my god, sorry, I can see very probably. It's t from t equals to 0, and then t equals to b, and then for the t we would plug in 0 and b, which I did in my next step. So 2 is still out. 2 limits from b to infinity equals to negative 1 over s e to the negative b s plus, well, it goes minus 1 over s e to the power of z, but you can just write it as a plus. And then the first function, it cancels out, because when it's e to the power of negative infinity, it equals 0. And then what we are just left with is a positive 1 over s, because e to the power of 0 cancels out to 1. And then we bring out our 2 that we saved. So when we multiply it, I don't know why it's a plus sign here. It should be a multiplication sign. It would equal to 2 over s for the, give me a second, for the s more than 0. Why s more than 0? Because if we put s equals to 0, it cannot be in the denominator. So we would have to have it s more than 0. And if s is less than 0, then integration wouldn't converge.
Converge, okay.
Converge, yeah, sorry.
All right, okay. Nice,
Thank you.
Thank you. Thank you, Ms. Katerina. I'm trying to upgrade the credits right away. Sometimes I don't forget. Okay, anyone else like to present? Anyone else has any questions? So I want to go back a little bit, because this couple of lectures are very intense. So let's see, 17. Let's go over a little bit. But they're all very important in mathematics. Gamma function, Bessel functions. Right. So Bessel's equation of order being non-negative have this kind of form. S squared as a coefficient of y double prime, x as a coefficient of y prime, x squared minus p squared. So p is a non-negative number. So the forces, so this one, so x squared minus p squared is the coefficient of y. And if we write in this one, in this form, we'll divide by x squared for every term, right, in this case. Right. And the solution for it is called Bessel's functions of order p. Okay, with this p. So this is our capital letter P. This is our capital letter Q. Right. This lowercase p is x times capital letter Q, P. So we get 1. This lowercase q is x squared times the capital Q. So x squared cancels 1 over x squared to be 1. So lowercase q is just x squared minus p squared. Right. the initial condition P of 0 is 1. Oops. What happened? Right, because P is a constant function, because P of any number is 1. And Q of 0 is just negative P squared. Okay. So we use the initial equations. Remember, the initial equations is R times R minus 1 times P naught times R. P naught, well, P naught is just P of 0, which is just 1 in this case. Then plus Q naught, right? Q naught in this case is just Q of 0, and this is negative P squared. So this is our initial equation. We simplify, in the end, we get R squared minus P squared equals 0. So now we solve these initial equations, we get R equals plus minus P. Right? Remember, we use this solution. We said, okay, one of the solution has this form, x raised by m plus r. Right? So R equals plus minus P. For this case, in this case, R equals plus minus P. Because this R we could think as x raised by r up front. Right? In that way, it may be easier to understand, where does this y come from? Y equals to x raised by r, then multiplied by this infinite sum. Then with this y, we take we find a y prime and a y double prime. Then we plug back into the equation. Then what do? We're trying to solve the coefficients. So how do we solve for the coefficients? We're trying to line up the exponents of the variables. If they do not line up, we have to force them to line up by changing the index, by re-index them. Once we re-index, we have to, sometimes if we have to consider the finite special cases. Right? For this case, we see this one has to be re-indexed to start from m equals 2 instead of m start from 0. Then by doing so, we have ignored m equals 0, m equals 1 in this case. So what do? We consider them separately. We consider m equals 0, what happens? M equals 1, what happens? And with the rest of m starting from 2, usually we can get a recursive relation. Then we have two solutions, r equals positive p, r equals negative p. Right? So we deal with each one individually. Then we find a recursive relation for p. So this, I really, but some of you already show some more work, right? But just make sure you can do this. Then when r equals negative p, we go through the same process, right? Go through the same process. So get our second solution. Then we talk about a famous gamma function. The definition of a gamma function is this. It's the integration from 0 to infinity, e to the negative t, t to the x minus 1 dt. Right? So the gamma function is in terms of x. So this dt works with this. You see, just cutting one dimension, infinitely many pieces. Right? A definition is defined for x being positive. So x can be positive integers or positive fractions. We have seen calculations of gamma function, right? Gamma 1, if we calculate it, we get a 1. Beautiful value. And we have this recursive relation, gamma of x plus 1 equals to x gamma of x. And using these two properties, A and B, and we can show like a gamma 5 is 4 factorial, gamma 6 is 5 factorial. So just gamma of, if x is a positive integer, not a fraction, so gamma of x plus 1, just x factorial. Right? You can see from this one, because gamma of x, you use this property, you keep writing gamma of x is x minus 1 times gamma of x minus 1. You keep going until 1. You see gamma of x plus 1 equals x factorial. A beautiful property. So here, gamma of 2, 1 factorial, gamma of 3, 2 factorial, gamma of 4, 3 factorial. And also we can calculate the gamma half, right, by going through the definitions. Going through the definitions, we see gamma half has a beautiful value. It's an irrational number, square root of pi. So this is a graph of gamma functions. Excuse me. Then we talk about the Bessel functions of first kind, right? And the solution to this one, again, corresponding to r equals to positive solution, is this. Just like this, right? We have seen before. Gamma of p plus m plus 1. We know this p plus m factorial. Right, change it around. So this is called the Bessel function of first kind of order p. So we denote with this jp of x. Yes, David?
On the final, would we have to memorize the series solution or of like the Bessel functions?
No, you don't have to. You know, the finals is something
like homework.
Like homework, right?
Okay.
Yes, right. Yeah.
Yeah, that would be scary.
No. Yeah, this is a similarly. So this is a beautiful relation, right? J prime of 0 order equals to negative of the first order. Bessel function of second kind of this. Oh, did I talk about this second kind? I don't even remember. Anyway, let's just go through now. So p is an integer, n. The solution, so to this would be C1, because p now is n, because usually we use n to representing counting numbers, right? C1 Jn of x plus C2 Yn of x. Well, Yn is very complicated writing, right? It's very complicated writing. So as you know, I'm not going to test you for the in the final, but just to know this. Okay, so such y of x is called the Bessel function of second kind of integral order, just to know it. Okay, Bessel function relationships. JP looks like this, you know. I don't even memorize this, so I'm not going to ask you to memorize this. But as long as we recognize, okay, when we see this, we know what this is. So we want to see, but we want to know the relationship. So we just see, I think Albert showed something about this relationship. So we see the order P minus 1, P,
I just
and
did
P.
a problem on that.
Yeah.
Yeah.
You did a P4, right? P equals to 4.
I did P4 in terms of P1 and P2.
Right.
I mean,
So you
J1.
see,
Yeah.
right.
J1 and J2.
Right. So they have this such beautiful relationship. Right. So this is all good to know.
Yes.
So
Very
this
good
one
to know.
can be, this one can be rewritten because this equals 0. This basically tells you, 3 consecutive orders have such beautiful relationship. Anshi, oh, Anshi's saying beautiful. I thought you have questions. Mathematics is beautiful. It's just amazing. Okay, there's examples. You go through yourself. So this is gamma and Bessel. Anyone has any questions? This is 17. Laplace transform. Well, if you want to go over previous any notes from previous, let me know. All right. Okay, Laplace transform.
Sorry, I have a quick question.
Yeah.
I think it's on homework 13. We're asking for the radius of convergence. It's just a general question. We don't need to look at specifics. When we do the ratio test, I remember if the ratio test results in 1, you can't use the ratio test, right? You have to use another test to test for divergence. So there's a homework question where R equals to 1. So I'm assuming what we need to do is find another test for divergence and confirm that it does diverge, and therefore it does not have a radius of convergence. Correct?
Right. Yes,
Okay.
you're right.
Okay,
Yeah.
thank you.
You're welcome. Okay. So Laplace transforms, and some of you showed beautifully done. Right. So we have this. We use capital letter F of S for the Laplace transformation of such function noted as lowercase f of t. Right. So this is this little f in terms of t. This is in terms of s. So let's look for the definition. This is the definition of Laplace transformation. And the f of t is in the integrand. And the integration is over t. Right? You could think a t as one of the axes. Right? So the t axis is being cut into infinitely many pieces. And then what's added into the integrand is e to the negative st. So variable is here. So the variable of capital letter F, which is s, is e to the negative st is here. you could see this last Laplace transform, gamma function, right? They all have a little bit of something similar. So this is e to the negative st, f of t dt. Okay, so I need you to remember this for the purpose of final exam, or maybe for your future graduate study. If you study mathematics, physics, or any science, because you need to know this. You need to use this. Then we have calculated a couple of it. So we have calculated Laplace transformation of one or of any constant. Well, we could just use C. F of t equals C. So that would be C over S for positive S. Right? Go through the definitions. So Laplace transformation of any number, any constant number, any natural number, I should say, right? Natural number n, Laplace of n equals n over s, for s being positive. Then we talk about this case, exponential function, e to the at. A is just some number. You can imagine e to the 3t, e to the 4t, e to the 5t, so on and so forth. So going through the Laplace definition, in the end, we get for s bigger than 8. For s bigger than 8. Okay, this a is here. A is the coefficient of t. For s bigger than a, we have this solution, 1 over s minus 8. The Laplace transformation of e to the at becomes a function of s, so 1 over s minus 8. Now we have seen some examples, right? E to the 4t, that's 1 over s minus 4. Or this is e to the 3t, that will be 1 over s minus 3, so on and so forth. This is another example, t to the 8th power. A, we like to be greater than negative 1. So going through the definition again, in the end, we get Laplace transformation of t to the 8th power, which is gamma of a plus 1 divided by s over s raised by a plus 1 for positive s. Right. So we have seen t to the t squared, right? T squared. So a equals 2. A equals 2. So gamma of 3, which is 2 factorial, which is 2, over s raised by 3. We have seen presentations. And Shu Xian did something very cute. He said t to the 0 power. Well, that's okay. So confirmed. T to the 0 power is 1, right? You can use this one, t to the 0 power, or you can use this constant. Do you need to memorize? And she's asking a question. Do we need to memorize common Laplace transformations? Yes, at least this couple I have kept talking about. Okay, the definition, because Laplace is just so important. The definition, transformation of 1, transformation of e to the at, that's just this. Transformation of t to the 8th power. Well, yeah, a lot of you use the linearity to put in your calculations. Right? You need to use linearity. This one to know, okay, I'm not going to put it in the final exam because gamma half equals square root of pi. This is very important and very famous. I don't know. You look this cute, you know, calculations. Cosine sine for hyperbolic. Okay, you know, only for you to know is good enough. Because some of you might not ever taking hyperbolic geometry.
Wait, sorry, I missed that. The cosh and the singe. Sorry, you said we don't need to?
Right.
Okay, okay.
You don't need to be troubled with this because I'm just afraid not all of you taking hyperbolic geometry yet. This is for hyperbolic geometry, not for Euclidean geometry. So not to worry about this. But you do need to know this transformation for this e to the ikt, right, follows from the previous. Because e to the at, a is just ik now. So just 1 over s minus ik. You know, it's fantastic. It works for this, right? And you know ik is not a real number, it's imaginary part. So transformation, Laplace transformation of cosine kt is s over s squared plus k squared. Laplace transformation of sine kt is k over s squared plus k squared. So the default one is s for cos, one is k for sine. Okay, so you know a final question may be something look like this. Then the inverse of Laplace. The inverse of Laplace. We know Laplace of t to the nth power is n factorial divided by s n plus 1. So that tells us the inverse of this is just t to the nth power. Right? We know Laplace transform the e to the at to 1 over s minus a, or the inverse of Laplace of 1 over s minus a, just e to the at. Laplace of cos kt is s over this s squared plus k squared. Once we are able to form in this case, so the inverse Laplace of this is just cosine kt. Right, so in this case, Laplace t cubed, that equals to 3 factorial, which is 6, divided by s raised by 3 plus 1, which is s raised by 4. Then Laplace of this, or here, right, here is the 1 over s raised by 4. Oh, okay, this is missing. Oh, here. Here's saying, okay, if we do t cubed divided by 6, that's 1 over s raised by 4. Basically, seeing Laplace inverse of Laplace of 1 over s raised by 4 is t cubed divided by 6. Laplace e to the 4t equals 1 over s minus a, or a is 4 here. So inverse of Laplace transformation of 1 over s minus 4, that has to be e to the 4t. Laplace of cos 2t, cos 2t, excuse me, equals s over s squared plus 2 squared, right? That's just s divided by s squared plus 4. Then if we have a Laplace, we want to transform 4 cosine 2t. So I have this 4 now. By linearity, this 4 comes outside of the Laplace. So it's just 4s divided by s squared plus 4. Then the inverse Laplace transformation of 4s over s squared plus 4 is just 4 cosine st. Anyone has any question? Okay, not to worry about piecewise functions for the final. All right, but you need to know this. Okay, it's good for yourself. But at least to know those 3 kind. Okay, Laplace transforms natural numbers to 1 over s for positive s. Laplace transfer t to the n equals n factorial divided by s raised by n plus 1. Laplace transforms cosine kt into s over s squared plus k squared, and sine kt into k divided by s squared plus k squared. Okay, at least this couple of transformations. Then yeah, then we have a lot of calculations with a couple of lectures. I think we have 3 lectures. Maybe we start with 15 or 14, 15. Yeah, first, so 14 is about solutions near ordinary points. Right. So we have these homogeneous differential equations. We call the coefficient before y double prime a of x, is a function of x. We call the coefficient before y prime a function of x. We call b of x, right? Coefficient for y, c of x. So basically, 3 coefficients, a function for x. And of course, they could be constant sometimes. But we want a of x not to be 0. Right? If a of x is 0, then this term disappears. And then when we divide by a of x, because it's not 0, and we get this form. So the rest of the class, we deal with p of s as a coefficient of y prime, q of x as a coefficient of y. So we made the coefficient of y double prime 1. So those are some examples. See, example like this. See, we divide by x squared because this is a of x, right? Then we see this 0 is not in the domain of this p of x. So we say, what do we see in our new language? In our new language, because we're dealing with differential equations, and solutions could be power series, right? So we use a word with power series. We don't talk about domain of a series. We talk about, if it's analytic at a point or not. So we use a new language. See, okay, 0 is not analytic for such p. So we learned the ordinary point. Right? What is the ordinary point? If a, so if P and Q are both analytic at A. You know, similarly to the language of, if you know, at this moment we can treat in P of X, Q of X, just a function of X, right? Because they look like a function of X, and they are a function of X. But we just use a new term because, you know, differential equations, solutions involves infinite series. So we use analytic. Or you can think this way, you know, if a number is in the domain of the function, so the function can be represented as a power series at the point. If that makes sense to you. So that's ordinary point. Okay. If the number or the point is in the domain of the function, we call it analytic, and then we call it ordinary point. Otherwise, we call singular point. Then we spend a lot of time talking about, you know, to recognize, because single point will have two kinds, regular singular point and irregular singular point. So those are some examples to find out if 0 is a singular point or ordinary point. So this chapter I think is easier, right? Just to determine solutions near ordinary point. Let's see if we have. Right, so I have some examples. The theorem says, okay, if A is the ordinary point of the equation for this, then, so that's to say P, Q are analytic at A, then the differential equation has two linearly dependent solutions of this form. Okay, what does that mean? That means the differential equation has two solutions can be represented by power series. That's why later on we're just using the solutions to be a power series. So that's by this theorem. Okay. So the rest is just examples. So that's 14. Then 15. We talk about the regular singular points. We have regular singular points and the irregular singular points. And the one famous solution is called the Frobenius method. Frobenius method. So those are some examples. Yes, David.
I have a question about the Frobenius method. Why is it that when you take the derivative of like the original y series, like y equals the series, that the index of the like incremented letter n doesn't go up as it does like as we originally did?
Okay, so in this case, look at this. We're dealing with the singular points. When we say, okay, let's see an example. Let's see this one. So this one started with x squared. So we put in this form, you see this is 1 over x. So 0 is not in the domain. So P of x is not analytic at 0. That's why, I'm not sure if I get your question. That's why, hold on. . That's why we multiply x. Oh, I don't get the form. That's why we have x over x raised by m plus r. M plus, no, I shouldn't say x plus x, m plus r. So we have x squared or x multiplied by the power series, but original y. Am I answering your question?
Yeah, so you're saying that the index is adjusted by the factors of x put in.
Exactly. Yes.
Okay. Yeah, thank you.
Yeah, you're welcome. Because we're dealing, if it's ordinary point, our y is just a normal power series. But we're dealing with we're dealing with singular points here. We're dealing with singular points here. Okay, let's see. So Frobenius method, a famous method. Right, regular singular point. If the lowercase p, remember lowercase p is x squared times capital letter, no, x times capital letter p, capital P of x. Q, little lowercase q is x squared times capital Q. So this is to say, if those two, when we multiply x and x squared, and they become analytic. So that becomes, so we call regular singular point. And if it's still not, we call irregular singular point. So dealing with this, we have a Frobenius method. Right. So what do? We just guess a solution to be y equals to x raised by r. Right. Then we differentiate. We have y prime, y double prime. So we plug back in. Then we try to solve for r. So we get r equals to, in this case, two numbers. The possibility of r could be two integers or integer and a fraction. So in this case, we get -2.5. So we think, y to the x raised by half or square root of x and 1 over x squared are solutions. But in general, so we do this where p, lowercase p, lowercase q are power series. So we have this x raised by r multiply by power series. So we can write it as x raised by n plus r. Then we introduce something called initial equation. Okay, initial equation as this: r times r minus 1 plus p of 0, we evaluating 0 for p of x, times r, evaluating q of 0. Okay, so this is our initial equation. We have this theorem says suppose 0 is a regular singular point, which means we manufacture the capital letter P into lowercase p by multiplying by x, the capital letter Q into lower little q by multiplying x squared. So if now we have, so if 0 is regular singular point of such, right? And let this row be a positive number. So we have this. So P of X, this is P of X. P of X is a power series. Q of X is some other power series. Because it's a regular singular point, a regular singular point means both lowercase p, lowercase q can be represented as a power series. And R1, R2 be real roots. So this is, I think this is type O of the initial equation. Then we can see something, all right? We can see A, B, two things. For positive X and the equation, the solution of the equation has such form. So we use this, right? X raised by R1, right? Or can be written as X raised by N plus R1 here. If the difference of the two roots is neither the 0 nor a positive integer, so, you know, this, so here is not 100% right, because, you know, which one is R1, which one is R2, right? And it has to be positive. And you know, when you do the questions, it's not so important. So there exists a second linear independent solution for positive X of such form. X raised by R2 with this. All right, so 2.
I have a quick question. If you go back up what you were talking about,
Okay.
the R given is 1 and 1/2. The condition they give is R1 is less than, no, R1 is greater or equal. It doesn't really matter the order, right? It's as long as one number
right.
is bigger. So if
Yeah.
R equal to 0, we can still use that. It's just the X in front of the summation would just become 1. It would just be summation of Cn X to the n, right?
That's true, yes.
Okay, thank you.
Yeah, I can't find the place anymore.
I think it's on page 8. Yeah, like the latter half.
Oh, right here.
Yeah,
Okay.
if you go down slightly. Yeah, there
Oh,
it
yeah,
is.
right here, yeah. Right here, right. Yeah, so this part ignore. This part just ignore. Yes, Su Xian.
Says like two rules, and then the possible Frobenius solution like y1 and y2. You have the power series inside an and bn. So how can I get that an and bn?
Oh, that's, remember we calculate, it depends. Depends on our calculation, right? Depends on each question.
Oh, okay.
Depends on each question.
No, so do you have a question for this one for the final? You just give us like a function and then figure out what's the y1 and y2. So do you have like example for that
For which
theorem
one?
approved for the y1 over x and then the like an
Not
something?
approved. Not approved, but we did have examples to use this.
Oh, where the example?
It should be down
let me match it. Let me match it. So I need to figure out what is an. So I was looking for what's an and bn for.
Okay. Let's see. So these two differ by an integer. So it doesn't have to be a positive integer. Just these two differ by an integer. This one just for just in general, there exists such one. So let's see examples. Let's see this one. Okay, you see this example? We get two solutions for R. R is -½ and 1. So by the theorem, we have a solution of x raised by R1 times the power series. And another solution is x raised by 1 times the power series. That's for the A part. So this example is just this one. Page 9.
Yeah, I got it, but could you like specify for AN and BN, you just and then the find out you use the initial rule?
Oh, for this one?
Yeah,
Oh, for
AN
this,
and BN.
no. For this one, no.
Oh, okay.
For this one, no.
So
We're
that's
not
why
able
so
to
I
do.
know and what is
Oh,
the
I
rule for
see.
the x powers and then the R for the integration equation.
Oh,
You just
I
find out
got you.
R1 and R2 and then the plugs in Y1 and Y2 something, but AN for the specialized the AN and BN was that. So okay, that's fine.
Yeah, we don't have enough like enough information for that at this moment to do that.
Okay, all
To
right.
do this A and B and just some coefficients. Just
I
some
got it,
coefficients.
but and then I just wondering, so, and then how can I get the AN? Because the power series you have the sum like a coefficient and then the products AN and BN like this. So how can I find it? Oh,
Right.
okay. You
So
don't
this
have.
is called a Frobenius solution. Frobenius solution is not like a definite, not definite. It's just a kind.
Okay.
Just this kind.
Okay. All right.
Good questions. Good questions. I see what you. But with some other, okay, now I see the R1 equals -½ R2 equals 1. Oh, hold on 1 second. Oh, you're talking about finding this AN, this BN, right? And hold on. So with this question, and we didn't finish yet. Okay, you see, when this is a solution, what do? We find y prime, y double prime, plugging back into this to find AN. Right? Okay, this is our first solution. To find AN, what do? We go back to this original equation. We find a y double prime, we find a y prime, we plug into this, we match up the exponent of x. In the theorem, just see this is this kind. The theorem says, okay. The theorem uses Pn and Qn, doesn't matter. Okay, just saying we have one kind of this solution, another kind of that solution. Oh, here. X raised by R1 times the power series, all right? But with a specific one, so this is a Y2, right? X raised by R2. With this specific one, so we do have a P, we do have a Q, right? As a specific one, we can always find AN or BN. So what do? We do y prime, differentiate y1, then differentiate y1 y1 prime again. So we plug back into this. We have done some examples. You have presented some. There's a lot of calculations. You have presented. Right, in this case, we say, okay, let's see this one, R1 equals -½ R2 equals to 1. Right, N plus R. It's the same as X raised by R time, X raised by R, then multiply by a normal power series. Right, you just take a derivative. Again, you plug back into the equation. Then you lined up with the exponents of x, because only when the exponents lined up with the equation equals 0, that says its coefficient adds up to be 0. So when we lined up the exponents of x of the variable, sometimes we'll have the reindex. If we have to reindex, we have to consider, because this reindex could go with 2, with 3, with 100. Then we have to deal with the individual cases separately. In this case, we reindex 2, starting from 0 to 2. So 0 needs to be 2, reindex. So we have to consider 0 case, we have to consider the 1 case. Then the rest of the case from 2, we need to find some patterns. So for R1 equals to -½ we find AN like this. AN has a relationship with n-2. So AN can be represented with AN-2 with such scalar 2 over n times 2n-3. Right, then we just evaluate some of these A's, try to find a pattern of it. In the end, we did find a pattern. So we find that the 2nth term has a relation with the first term. What's the relation? The relation is 1 over n factorial with this. So, in final exam, if I put if I have to test you using Frobenius method, probably I have to make a simple one, not as so complicated, right? Because this takes time. For homework is okay, but for exam, it takes too much time. For the second solution 1, you do the same thing. Right? Try to figure out a relation by evaluating some numbers. Then you find the pattern. You form nth term. So then general solution, put it back in, right? Put it back in the AN, put it back in the BN, you get a general solution. Because even find the 0 order, it's a lot of work. I don't know, I have to consider that, how to do. What about the Frobenius method? But Frobenius method is a famous method in solving differential equations. Bessel's function surely will be in the final exam. Probably I have to give you this, right? Give you the 0 order. So that's Frobenius and Bessel's. So this is 15, then 16. Talking about the 2 solutions differ by an integer. We see an example is differ by a fraction. So this case differ by an integer. We have 2 cases. One is non-log. Right. By solving the initial equations, get using this, the power series with x raised by n plus r, because we're dealing with a regular singular point. So we have this extra plus r. Then, differentiate ay, then differentiate y prime, plug back in, lined up the exponents of x, solving for the coefficients of the term. Then try to find a relation in between among the terms. So this is nice. So this is nth term has a relation with n minus 1's term. Right. So see in this case we'll find a relation Cn with the second terms. So the solution looks like this. So this is for Frobenius series solution. I'm not sure if I'm able to make a simple one for Frobenius method. Okay, the second one is log case. First one is a non-log case. Second one involves logs. So let's see this theorem. So suppose 0, it doesn't have to be 0, but 0 is a simple case, right? It's a regular singular point of this. And R1, R2 be the roots for the initial equations. So first case is the two solutions are the same, which means we get a perfect square. Then we have two solutions. Y1 is this, x raised by R1, right? Or we can think as x raised by n plus the solution. The second solution is y1, which is the first solution, multiplied by log x. Then plus this piece, x raised by the solution plus 1. Or we can push this one inside to become the power of x becomes x raised by n plus r1 plus 1. Right? This is plus a root because those two roots are the same. So if R1, R2 differ by non-positive integer or counting number, so Y1 is still this, and now Y2 just differ from the previous one, has this scalar. Because in the first case, there's no scalar here, 1, in front of Y1 of x. That's when R1 equals R2. When R1 and R2 are differ by the positive integer, so I have this C, and the rest of it are the same. Oh, of course, different here. Because the first one we have x raised by R1, this one is the same. But the second one is different because those ones are different. Those R1 and R2 are different. So this second piece is x raised by R2. It's not x raised by R1. But in the first case, because the two roots are the same, so this is still x raised by R1, right? R1 equals R2. Then following some examples. So this couple of lectures are very calculation heavy. Yes, David.
I don't quite understand what makes something a logarithmic case. Like what sets it apart from the non-logarithmic case again?
Oh, one is involved with fractions. When the two roots are not, the both roots are not both positive, not both integers.
Okay, so they're negative. They're both negative.
They both that can be negative or can be positive, but the one case is involves the fractions.
For the logarithmic?
For the non-one.
For the non-logarithmic, yes.
Right.
Like r equals fraction.
Right.
And so if there are no fractions, then it's logarithmic?
That's right.
Huh, okay. Thank you.
Okay.
I didn't
You're
notice
welcome.
that actually, now that you mention it.
Oh, okay.
Yeah.
So this is a good review. Because I figured it's very heavy in calculation, this couple of.
Yes.
Yeah.
Took me a long time, some of them.
Yeah, so I was thinking, okay, tonight probably I won't go further, just go backwards. 14, 15, 16. Yes, that's why I'm thinking, okay, let's do a little bit of review. Okay, so that's 16. I think I did talk about 17 already, right? But just in any case, let me know if anyone has any questions. So, 14, 15, 16, 17 are all very kind of heavy. Yes, Shuxian.
Could you repeat like a non-log and log? So what's the like R1 and R2? You're talking about the
Okay.
fraction
Let's go
something,
back.
but I didn't get it. But you just talking about the R1 and R2 is fraction is non-log, or
Let's go back. Let's go back. Let's see it, right? So we can. So 16. So two cases. Yeah. For the regular singular point, are we here? Okay. Am I in the right place? No. No. Log, non-log. I think I'm in the wrong place. This is a 16. Is on 15? It's on 16. Oh, here. This is my third class for today. My brain is like probably only halfly working. Can we have extension on homework 5? Yes. November 10th, maybe? Yes. Yes, you should get some extension for homework. It's on notes 16, right? Why I couldn't find it?
Page 10?
Page 10, you found it already? Okay, 16, right?
Yeah, 16. The first
Okay.
page is not non-log. So could you just explain so R1 and R2? How can I figure out it's non-log and log? So that's
Log. Okay. Oh, page, which page? David was mentioning page number.
10.
10. Page 10. 8, almost there. Page 9. Page 10. Okay, we're here. All right. No, I made a mistake. David, what was I saying? I said non-log is for fraction, right? That's not true.
Yeah.
Because for fraction, we use the Frobenius method. The non-log is not for fractions. Non-log is for differ by integers. Either the two roots are the same, or the two roots are differ by an integer.
I had a question about that because if you look on page
Yeah.
5, there's an example where r equals -1 and 3, and they just use the regular Frobenius method.
Let's see, 5. Where is 5? 5 is here. Oh, can you repeat your question?
Yeah, so you said the logarithmic case is for if the r's differ by an integer, but here the r's would differ by an integer. See, the r's are, if you scroll down a little bit, r equals -1 and r equals 3.
R equals 1, -1 and 3, right?
Yes.
Yes, that means we could use that.
Can you use logarithmic?
Yeah.
Oh.
Yeah.
So
Yeah,
do
some of
you,
them are different methods.
is there ever a time when you're forced to use the logarithmic method, or can you use it like as an option?
You can use it as an option.
Okay, so there's never a point which you have to use it.
Oh, I don't think so. I just don't recall right now at this moment.
Okay.
Can use different method, as long as the situation fits the theorem, you can apply the theorem, you can use different methods for it.
Yeah, because on the homework I was waiting to get a question where like I would have to use the logarithmic case, but I don't think I ever yeah.
I see. No. Okay. Good questions. Good questions. Okay, okay. Oh, and she thinks it's shortcut. Yeah. Okay. Okay, so this is log. Log is different by integer. Non-log. Okay, good questions. Okay, David, you asked a good question. No, I don't have an answer for you. Let's see, maybe let's try that. Let's try to solve this one, use this one for log case. Then try the log case with a non-log case. Because even specified as like R1 is bigger than R2, but which one to see is R1, which one to see is R2. Yeah, I don't think it has to be. You know what? I think about it. I think about this too. To see if there anything forced to be used, this one, but not the non-log one, or forced to use the non-log one, not this one. Okay, I just don't recall anything now at this moment. My brain doesn't work anymore. Okay, that's for tonight, and I will extend the homework. All right, so the homework, you can always submit your homework. Even it's late, you still get the credits. But for those couple of lectures, I will extend them because I don't count any. So 14, 15, 16, 17. All right, you can still submit them because it's just the calculations are heavy. All right, anyone has any questions?
I just have like one quick question. So in
Yes.
general, when you're using the Frobenius method, you want a regular singular point, right?
That's right.
Okay. And for like the general use of the series, you just need, it's just a regular point, right? Or ordinary point, sorry.
Yes, right. Because we separate, we talk about if it's an ordinary point, it's just the normal. We don't need any of these methods. For regular singular point, we have using those methods. Frobenius methods, the log, non-log.
Okay, thank you. Thank you.
You're welcome. Thank you, Liz. Have a good night.
All right, have a nice night.
Professor,